All right, welcome to Physics 2425, Lecture 9, Impulse and Momentum. So we're moving on to another way to analyze motion. So we started with kinematics, looking at position, velocity, acceleration over time. Then we looked at forces and Newton's laws for why those positions and velocities and accelerations change. And then we looked at energy, the transfers between kinetic and potential energy, while an object goes through its motion. Now we're looking at momentum, and momentum is also related to motion, but here we can talk more about multiple object systems in which momentum is transferred between different objects. So the definition of linear momentum is mass times velocity. So that's really all momentum is. So if you take momentum as a vector, p here, that is a lowercase p, and then mass is a scalar and velocity is a vector. So any object that is moving has momentum. The momentum is larger the more mass the object has and the higher the speed of the object. Now, because momentum is a vector and velocity is a vector, but mass is a scalar, the direction of momentum is always in the direction of the velocity. Momentum has an SI unit of kilogram meter per second, sometimes just written kgm/s. That dot isn't always shown. It's just a multiplication symbol, just showing that the kg and the m are multiplied together. They did not name this, kind of like a Newton is 1 kilogram meter per second squared. But momentum was not given a special symbol for this. Momentum as a vector can therefore have components in the x, y, and z direction. Mass isn't a vector, so the mass is the same in all three of these. And then the magnitude of the momentum would just be the square root of px squared plus by squared plus pz squared. So you can use both magnitude for that. Most often we'll be working in 2 dimensions, not 3 dimensions, but it is a 3-dimensional quantity. So we're going to take a look at how linear momentum and kinetic energy are related. So linear momentum is defined as P is equal to m times v. We're just going to look at the magnitudes for now. We're going to assume this is in 1 dimension. Our kinetic energy is equal to 1/2 mv squared. So both of these quantities depend on mass and speed, but in kinetic energy, the speed is squared. So having a difference in speeds will create a large difference in kinetic energy. So we have 2 different objects with 2 different masses. We don't really know anything about it. We're just going to kind of create a model, and we want to figure out how do their momenta compare if they have the same kinetic energy. So we have object 1 is going to have a momentum of m1 v1, and it's going to have a kinetic energy equal to 1/2 m1 v1 squared. Our second object is going to have a momentum of p2 is equal to m2 v2, and a kinetic energy k2 of 1/2 m1 m2 v2 squared. So I want to compare these 2 different momentums. The problem is that all my variables are different. There's not really an easy way to compare that. So I need to find a way to get one momentum in terms of the other. So for example, these kinetic energies are equal. So I can sub in K1 for K2. So I get 1/2 m1 v1 squared is equal to 1/2 m2 v2 squared. And then from here we can see that the 1/2s are going to cancel. And then what I could do with this is say solve for v2. Since v2 is unknown and it's a very unknown quantity, I can find that v2 squared will be m1 over m2 times v1 squared. And then to find V2 itself, I can take the square root of both sides. And so that's going to give me V2 is equal to the square root of M1 over M2 times V1. So that gives me an expression for V2. So then what I can do is I can come over and I could take that V2 and plug it in over here. So then I can, now that I have an expression for the velocity of the second object, I can put that in for the momentum. So my momentum of the second object is going to be M2 times the square root of M1 over M2 times V1. So I don't like having M2 in two different locations. So one of my favorite little tricks is I can square and then take the square root of that M2, and that allows me to combine the square roots. So I get that P2 is going to be M1 times M2 squared over M2 all square rooted times V1. So then I can simplify that by canceling the square and the M2 on the bottom. And so that find P2 is equal to the square root of M1 M2 times V1. Well, I want to compare P2 and P1. So what I'm going to do is I'm actually going to solve this for V1. So I get V1 is going to be P2 over the square root of M1 times M2. And then I can actually take that and I can go over and plug that in way over here for my V1 in my momentum for object 1. So I get P1 is equal to M1 times P2 over the square root of M1 times M2. And then I'll do my little trick again and get those masses combined, those M1s. So I'm going to square and then take the square root. So I'm going to get that P1 is equal to the square root of M1 squared over M1 M2 times P2. And then simplifying down, I can once again cross out one of those M1s. And so I get that P1 is equal to the square root of M1 over M2 times P2. So this equation basically says that how momentum 1 and momentum 2 are related is going to be based on the square root of the ratio of their masses. So I can see that, for example, if M1 is equal to twice M2, then what's going to happen if I plug that in, P1 is going to be the square root of 2 times M2 over M2 times P2. So if I was to say have that, those M2s would cancel, and that would give me that P1 would be the square root of 2 times P2. And since the square root of 2 is not something I have memorized, is approximately 1.4. Square root of 2 is bigger than 1. That tells me that P1 has to be bigger than P2, but it's not double. Okay, so if they have the same kinetic energies, then the object with the larger mass is going to have more momentum, but the momentum isn't going to be double with the mass. So this kind of gives you a way to see that objects can have the same kinetic energy but different momenta, and the way that kind of velocity squared in that kinetic energy term varies compared to the linear momentum. So often what we do is we talk about the change in momentum, how momentum changes over time. So change in momentum is defined as delta P. And anytime you're using delta, it's always end minus start. So delta P in this case could like be P after P2 minus P before P1. So you can substitute in M and V after and M and V before. And then because if you're assuming here the mass is the same, then you could pull out the m. So this is a very common way to express change in momentum for a single object. You'll see that when we get to collisions, that collision's a little more complicated, and because we have multiple masses, you might have to modify the equations a little bit. So if we look at two objects here, so for example, the teddy bear and the ball, we're assuming that they are being dropped from the exact same height. We can assume that they start at some particular v, so they're moving at the same speed at this first instant. So this is our first instant here, and then as the teddy bear falls, it's going to fall and it's going to come to rest. It's just going to squish, whereas the ball is going to bounce back upwards. So we're going to assume that this collision with the floor is so that way the ball rebounds with the same speed that it had before. It's just now changed directions. So when you look at the change in momentum using this equation, for the teddy bear, it's going to be delta P is going to be m. If we assume they have the same mass, then you can compare their momentum here. So you're going to use v after. Well, the teddy bear ends at rest. And then you subtract the initial velocity. Well, our initial velocity, if our positive y direction is upwards, this velocity is initially negative. So it starts with a negative velocity, so then the negatives cancel, and that gives us a change in momentum of mv. For the ball actually ends with a positive v, so it ends going up, and then when you subtract that starting, it's also having that negative velocity at the start. So those negatives cancel, and we end up with m times v plus v, which is the same thing as 2v. So you end up with 2mv. So when you look at the change in momentum, whenever an object actually rebounds and goes in the opposite direction that it did before, that is always going to be a very large change in momentum. Now, when we're also looking at change in momentum, it's very rare that an object actually rebounds in one dimension. Most often what happens is that objects will rebound at angles. So momentum is a vector, which means that momentum can be conserved or calculated in 1 dimension, 2 dimension, or 3 dimension. So for example, in this problem, we have a momentum coming in at the start here at an angle of theta. And so you're going to have this collision, and they're giving us the perpendicular here to compare, and you're going to assume that it rebounds back with the exact same angle, but in the opposite direction. So if you wanted to calculate the change in momentum, we would say that the change in momentum, because it's a vector, is going to be momentum 2 minus momentum 1. But momentum 2 and momentum 1 have 2 different components. So for example, P2 is actually going to be P2x plus P2y. And then you're going to have your momentum at the start is going to be P1x plus P1y. Now, in unit vectors, you could join those components together, and that's what they've done over here, is they've shown that P2x, you can look at the x components separately, and then you can look at the y components separately. So what you can do is you can separate these. So your delta P is going to have a delta P in the x direction, which is going to be P2x minus P1x. And then delta P in the y direction is going to be P2y minus P1y. Now the next topic we need to discuss is what happens when you have a system of objects. So we can talk about the linear momentum of a single object or for multiple objects. And so when we're looking at multiple objects, we can define the momentum of a system, and the momentum of the system For the system of objects, our total momentum is basically just going to be a vector sum of the momentum of each object. So this right here represents the momentum of the system. So for example, we have P1, P2, and P3 based on these three different objects. So what you could do is you could then add up the momentum of the system and talk about this collectively. So this is often what happens when you're talking about things like explosions, where maybe an object is here together and then maybe it blows apart and it breaks up into different pieces and each piece moves off in a different direction. Or you could talk about the momentum of an atom. Think about an atom. You've got your nucleus here, and then you've got all these like electrons that are like moving around in all directions, and then they have a momentum together. Or you could think of like gas particles. So you've got a whole bunch of like oxygen molecules moving around all different directions, and we want to know what the net momentum of all of that is. Lots of reasons why we might talk about the momentum of the system. Well, in this case, it's just another case of vector addition. So what you would do is you would add the x components of each of these three. So P3 here in this case only has a y component. So the net momentum of the system in the y direction is going to be based only on P3. And then the x components are going to be based both on P2 and P1. So for example, the momentum of my system here is going to be the momentum of object 1 plus the momentum of object 2 plus the momentum of object 3. But I can break those into components. So I can say momentum of the system in the x direction is going to be P1x plus P2 x plus P3x. So P1x is going to be a positive 5 kilogram meters per second. P2x is going to be a negative 8 kilogram meter per second. And P3x is going to be 0. So we can neglect that one. So the momentum of my system in the x direction is going to be P1x, which is a positive 5 kilogram meter per second. And then I would add a negative 8 kilogram meter per second for object 2. So this gives us the momentum of the system in the x direction is going to be negative 3 kilogram meter per second. So it's going to be the left at 3 kilogram meters per second. And so that's what this is showing right here. So we have a momentum to the left of 3 kilogram meter per second. We could also then find the momentum of the system in the y direction, and that's going to be P1y plus P2y plus P3y. But only P3 has a y component, so those two are both 0. So the momentum of our system in the y direction is just going to be P3y, which is therefore just going to be a positive 4.0 kilogram meter per second. And so that's what they're showing here as Py. And then the momentum of the system, we can then, of course, use the Pythagorean theorem to relate those. So the momentum of the system, the magnitude is going to be the square root of Px squared plus Py squared. There's our P system x and P system y. And then when you do that, it's basically a 3, 4, 5 triangle. So the net momentum of the system is 5 kilogram meter per second. And then you could calculate the angle theta as tan to the minus 1 of Py over Px. And then that's where the 53 degrees comes from. So you could find the total momentum of that system of particles. Okay, and they can be moving in 3 dimensions, not just 2 dimensions. So now, what is causing those changes in momentum? Well, we really have to go back to Newton's laws, because Newton's laws are what describe the interactions between objects and forces and so forth. So Newton's second law says that our net force is equal to mass times acceleration. Well, let's do a little manipulation. I want to get this in terms of momentum. So what I can do is I can substitute in my definition of acceleration, which is change in velocity over change in time. And then if I multiply and distribute that mass to both terms, I get mv minus mv0. Well, those are just momenta. So P here is m times v. That's the momentum at some time. And then mv0 is going to be our momentum at the start. Well, that's end minus start. That's just change in momentum. So we can put Newton's second law in terms of momentum. And actually, that's how Newton originally intended this equation to be, was actually in terms of momentum. So this is Newton's second law in terms of momentum. It says that net forces cause changes in momentum over time. Now, one thing we need to be careful with this, this is usually talking about external forces, because we just talked about systems of particles. So I could write this a little more specifically as the change in momentum of a system over time is equal to the net external force. So if we rearrange this, so if we take our net force is equal to change in momentum over change in time, but we multiply delta t to the other side, then what we end up with is a statement that says that our change in momentum is equal to the net force times time. In this case, it's an average force. That's because impulse can be defined as an integral. And this product of force and time is defined as impulse. So impulse describes how forces applied over time cause changes in momentum. So the larger the force applied and the longer the force is applied, the bigger the change in momentum is going to be. So I like to think of impulse as kind of the way that objects change. So picture that you have an out of control bus or something. It's like Speed or something like that. I don't know. It's like a Superman. Okay. If you have this bus or whatever moving very, very fast at a high speed. So it has this speed. So it's going to have this momentum here. And it needs to, or it needs to come to stop. Okay. Before, say, it hits this wall. So a superhero might come in with his cape and try and stop the bus. Now, if that superhero is like Superman, maybe he's strong enough to basically just bring that bus to stop right at that instant. He sticks out his hand, the bus stops, the bus crumples, the people continue forward, and basically everybody dies. The reason is that if that bus comes to stop in basically a time that approaches zero, then that change in momentum is going to have a very large force in order to cause that change in momentum. That would cause serious injury to everybody involved. Instead, if Superman was smart and wanted to save the passengers in the bus, he would maybe allow his feet to skid or his flying to skid, so that way the collision takes a longer period of time, and then the smaller the amount of time is, or sorry, the larger the amount of time is, the smaller the force needs to be in order to cause that exact same change of momentum. That's why we have airbags. Airbags provide a cushion so that when your head slams into it, you have to basically crumple the cushion first before your head comes to rest. That is going to increase the time of collision and therefore reduce the force to cause that change in momentum. Now, the force that's being applied to change that momentum is often rarely constant. So for example, this over here is a graph of force and time. So the previous equation that defined impulse as F average times delta t only gives you an average value over that time interval. If we want to say find an impulse at any one instant in time, we would have to know what was going on or over a particular time interval. So say we have a function here, f of t, that describes the force over time. If you use f average t, then basically what you're doing is you're finding, okay, your average value here applied over the time and assuming that that is constant. If you take f average times t, that's approximately the same thing as taking the area under the curve of this graph, but assuming that the graph was horizontal. Well, in calculus, the process of taking an area under the curve is integration. So therefore, the actual definition in one of its most precise forms is going to be the integral between t1 and t2 of f net delta dt. So therefore, that would be finding, say, the area under the curve of this whole function here. And the area under the curve of this guy is going to equal the impulse on that interval. Now, when you look at this impulse, that impulse is going to be applied in a particular dimension. So this could have forces in multiple dimensions. These are vectors. So these could be forces causing changes in impulses in 1, 2, or 3 dimensions. You'll most likely can see these in one-dimensional problems though. So you can therefore integrate the force over time, assuming you have force as a function of time. If the force is constant, then the force could get pulled out in front of that integral. And when you do that, that is just going to give you that J impulse is going to be F times the integral of dt from t1 to t2, which is just going to give you F times delta t again, which brings us back to our previous definition of impulse as force applied over time. So either way, you can find impulse by using the area under the curve or by integrating a function. Just be careful because this definition only works if F is constant. Otherwise, it gives you the average force. So here is that example of like the safety features, seat belts and airbags. So you can take a look at this, pause the video, and kind of look over this example a little bit more on your own. Now, energy can be conserved. Energy is conserved if there are no non-conservative forces. So if as long as there's not something like friction or whatever, as long as we're dealing with gravity, spring force, when we get to physics 2, you'll see things like electric potential energy. There's different types of potential energy that can be conserved and then transformed into, say, kinetic energy. Well, momentum can also be conserved, but there's a different set of circumstances under which momentum is conserved. And first of all, you have to have 2 objects in the system. If you only have 1 object in your system, it's impossible for momentum to be conserved, because any change in momentum is, if it's isolated, is not going to have a chance. So whenever you're doing conservation of momentum, you're going to have at least a 2-object system, and you make sure that your system is always the objects involved in the collision. So in this case, we're going to define our system here to be just those 2 balls. So this only works if there are no external forces on the system, and as long as there's no mass entering or leaving the system. You have to just kind of be aware. In a lot of cases, if they tell you it's a frictionless system and there's two balls or 2 cars involved or something like that, you can generally assume that the momentum is going to be conserved. But if there's definitely friction involved, then you might not have conservation of momentum. So it's a good idea to start any problem off that you're going to use by saying, assuming that momentum is conserved. You can write something like that. And then you can go through and then solve your problem. Okay. But what conservation of momentum will allow us to do is it will allow us to find the velocities of different objects before and after collisions. So taking a look at our definition of Newton's second law, we have our net external force is equal to the change in momentum over time. So if that net external force is equal to 0, then that means the change in momentum over time is 0. And as long as your time is finite, then that means that the numerator change in momentum has to be 0, which tells us the momentum of the system at the start has to equal the momentum of the system of the end. Okay, and as a reminder, you want to make sure you define the system to be the objects directly involved in the collision. So times when momentum might not be conserved, at least linear momentum, is if you have an object that is fixed in place. So for example, if I have a wall here, and I have a ball collide with the wall, the ball could say bounce off and change momentum, but if that wall is fixed in place, then it's not gaining whatever momentum is lost by that ball, because it starts with positive momentum, and then in the end it ends with negative momentum. So there was definitely a change of momentum for the ball, but the wall does not move to keep up that momentum. So momentum is being lost from our ball wall system. Why would that momentum be lost? Well, it'd be lost because, well, that wall has to be attached to the floor. It's probably attached to the ceiling. That floor is then attached to the rest of the building. And so basically the wall is not isolated. The wall has external forces on it that are not acting equally and oppositely, and therefore cause that loss of momentum from the system. But if the objects, like the balls, are free to move and they're free to bounce off of each other and on that frictionless surface, if the objects are free to move and change, then you're generally going to have your linear momentum conserved. So here's an example. So we have two masses, M1 and M2, that are connected by both a string and a spring. So these are both starting at rest. So if we assume that these are starting at rest, then the momentum of my system at the start is 0. So that means after the collision, or in this case, after the explosion, this is a physics explosion, if you burn the string and the spring starts out compressed, then basically what happens, think about energy, is this elastic potential energy that is stored in that spring is going to convert to kinetic energy for those two masses. But these masses need to move, assuming this is a frictionless surface, to keep that momentum the same, so that the momentum at the system at the end is also 0. Because if our momentum's conserved, if we have no momentum at the start, we have to have no momentum at the end. So that means these two velocities after the collision cannot be equal. So you could say set up an equation using this assumption that my momentum, my system, has to equal the momentum of object 1 plus the momentum of object 2. So momentum 1 is going to have to be m1 v1, and momentum 2 is going to be m2 times v2. So if I was to say wanting to find v2 and see how it compares to v1, I would get that negative m1 v1 is equal to m2 v2, and then v2 would need to equal negative m1 over m2 times v1. So I could see here that if m1 is larger than m2, then that means that v2 must be larger than v1, and it must also be in the opposite direction, because the negative here really just means opposite. So this would allow you then, if you know the masses, it would allow you to figure out at least the ratio of velocities. Given more information, you might be able to say find some of those missing values as well. So we can summarize this by saying that the change in momentum of one object has to be equal and opposite to the change in momentum of the other object. Okay, so whatever momentum is lost by M1 is gained by. So let's take a look at an example problem. So an archer stands at rest on frictionless ice. So we're gonna have an archer here on some frictionless ice. And he's gonna fire a 0.5 kilogram arrow horizontally at 50 meters per second. We have the combined mass of the archer and the bow is 60 kilograms. So we're gonna define our system as consisting of the archer with the bow and the arrow. So our initial state is both the archer and the arrow are at rest. Later on, at some unknown time, they didn't give us the amount of time, the arrow over here is moving with a speed of 50.0 meters per second. Well, if it has a mass and a momentum going to the right, then in order for our momentum to be zero at the start, that means that the archer with the bow has to go backwards with some unknown velocity. And that's what we want to find. Now we know that the mass of the arrow is 0.5 kilograms. And we know that the mass of the archer and bow together is 60 kilograms. So we can write an equation that says the momentum of our system at the start has to equal the momentum of our system at the end. The momentum of our system at the start is 0. The momentum of our system at the end is going to be the momentum of A plus the momentum of B. Momentum of A is going to be MA times VA. The momentum of object B is going to be MB times VB. Well, we're looking for the velocity that the archer moves, so that's going to be VB. So I'm going to solve for VB. So I'm going to get negative MAVA is equal to MBVB. So then solving for VB, VB is going to be negative MA over MB times VA. We can plug in negative 0.5 kilograms divided by 60.0 kilograms times a velocity of 50 meters per second. And plugging that in gives us a speed VB equal to negative 0.42 meters per second. So you can see that the negative just tells us that the archer is going to the left, which makes sense, okay? It would be that rebound effect because the bow is exerting a forward force on the arrow, so the arrow exerting a backwards force on the bow, so it's getting pushed backwards. But you can see that the magnitude, that 0.42 meters per second, is much smaller than the arrow, and that's because of the difference in masses. So you can see that although they have equal momentums, the arrow and then the archer and bow, they have to have equal and opposite momentums in order for have the system equal to 0. But that does not mean their velocities have to be anywhere near similar. So now we can also classify these different types of collisions in terms of what happens with kinetic energy. So we define collisions as two types. We can have elastic collisions and we can have inelastic collisions. These are two general categories of collisions. Now, we assume that momentum is conserved if there's no net external forces. So we can have momentum conserved in both elastic and inelastic collisions. We could also have momentum not conserved in elastic and inelastic collisions. Whether a collision is elastic or inelastic is due only to what happens to kinetic energy. In real life, there is no such thing as an elastic collision. These do not exist. And that's because we would have to have a perfectly isolated system so that any kinetic energy changes you have are only between the objects in the system. So an elastic collision has the same amount of kinetic energy before and after. So basically, delta K is equal to 0. In order for this to happen, there'd have to be no energy lost to heat, no energy lost to sound, no internal energy created by vibrations inside, because internal energy is not going to be kinetic energy. So all real collisions are elastic. However, a lot of collisions are close enough to being elastic that it's a good approximation, and it can give us more information about our system. For example, if I have a gas and we wanted to look at the temperature of the gas. From chemistry, if you've gone through your chemistry courses, you probably talked about kinetic molecular theory. One of the assumptions of kinetic molecular theory is that collisions are elastic. So that way, if a gas molecule bounces off of the wall of a container, that it keeps its momentum and it keeps its kinetic energy. Just changes, well, I guess it keeps its kinetic energy. Its momentum changes directions, but basically it keeps that speed with that collision. So there are reasons why we might assume elastic collisions, but all real collisions are inelastic. And in inelastic collisions, our kinetic energy is not conserved. So there's gonna be some loss. Now there's two special cases, and one case is the perfectly inelastic. This basically is anytime objects stick together. If you have objects stick together at all, a bug colliding with the windshield of a car, catching a ball in playing sports, anytime the objects stick together, you are always going to have a loss of energy, because in order for those objects to stick together, if you think about the surfaces of those two objects, you have molecules all along the surfaces of those two objects. And those molecules are exerting intermolecular forces on each other. Once again, kind of going into chemistry and kind of where these forces come from. So by putting those together, they are getting forces and attraction in between, which is creating internal energy in order to hold those together. That internal energy comes from a small amount of lost kinetic energy, or sometimes a lot of lost kinetic energy, especially if the collision causes vibrations and causes those molecules to kind of vibrate inside. So you're going to lose kinetic energy anytime objects stick together. On the other hand, explosions in physics are whenever you actually get a gain of kinetic energy. So anytime objects start together and end apart, kind of like our example with our bow and arrow on the previous slide, if your objects start together and they have no momentum at the start, and then they separate, okay, if they're going to separate and they're going to move, you had no momentum, no kinetic energy at the start, and then they start moving, that's going to cause an increase in kinetic energy. That's going to be inelastic because you did not have zero change in kinetic energy. Now, where does that energy come from? Well, if we look at this previous case, it would come from the energy stored in the bow. If we look at this case over here, we'd have energy stored in the spring. If you think of a firework is going to have chemical energy. You're going to have a chemical reaction occur with that added heat also going in and kind of accelerating that collision. So the reason we would use this is, first of all, to figure out how close to our ideal version is it. So we might figure that out. How close to ideal do we have? Otherwise, we might assume that a collision is elastic, because what it allows us to do is it allows us to create two sets of equations. Conservation of momentum, which involves mass and velocity, and conservation of kinetic energy, which involves mass and velocity. So this would allow us to have more unknowns that we can solve. So for example, we could have two known masses and two unknown velocities. Without elastic collisions, we would have to know the velocity of one of our unknown objects in order to actually find the velocity of the other. But we have to be careful. We can never assume a collision is elastic unless it's stated in the problem, because it doesn't actually exist and it will cause problems. So what we can do is set up equations. So anytime you are solving problems with collisions, we're most often going to assume that momentum is conserved, unless you have a case where one of your objects is fixed, like we said with the wall and the ball. In which case you can have an elastic collision with the ball and the wall. It would be elastic if V1 and V2 were equal, because the kinetic energy you would have at the start would be 1/2 mv1 squared. Kinetic energy at the end would be 1/2 mv2 squared. And because of the square, the direction doesn't matter. Your kinetic energy at the start and at the end could be the same. So it's possible to have only kinetic energy conserved if they tell you that's an elastic collision, or they tell you the velocities are the same and you haven't lost any mass. And if you have those situations where the objects are moving on this frictionless surface and they're both free to move, you have conservation momentum. But then if they have situation like this, where the two objects are both free to move and they tell you it's elastic, it's possible you have both at the same time. So you can either have just conservation momentum or just conservation of kinetic energy, or a combination of both. The way I solve these problems is I write a conservation momentum equation. So saying I have objects A and B, and I have possible velocities at the start and at the end for both. And then I have a kinetic energy equation here. So you can set up all sorts of problems with this. And you can also combine these with two-dimensional problems, because you could set up a conservation momentum in the x direction, and you could then set up a conservation momentum in the y direction. Kinetic energy is a scalar, so there would only be one equation. So it's possible, if you're doing a two-dimensional problem that's elastic, that you could actually have three unknowns, because you could have an x equation, a y equation, and then a kinetic energy equation. So the algebra can get complicated really quickly. So to kind of help you with these types of problems, I have a bunch of problems. So here, right here, this one is a 2D elastic collision problem. So this is like the worst of the worst. Well, I don't think I gave it the worst of the worst, but this involves the fact that you have an elastic collision in 2 dimensions. So you have an equation for momentum in the x equation, y, a momentum in the y, and a kinetic energy equation. So you could have 3 unknowns. I also have a perfectly inelastic collision example problem and a ballistic pendulum problem solving example, and then some other videos that you can help if you are struggling. A ballistic pendulum, these are some of my favorite. This is, for example, if you take a pendulum and you pull it back so that it swings, and then maybe that pendulum hits a second object, which then launches it. You'd have momentum conserved in the x direction, but not in the y direction. So these types of problems are pretty fun, because you can have conservation of energy during the swing, and then during the collision itself, you could have conservation of momentum in the x direction. And then maybe this guy bounces backwards, and you could figure out, well, how far does it swing? Or maybe these stick together and they swing together. Lots of different options that you can have for collisions. So please, please, please actually take some time to watch some additional problem solving videos to see more how you would solve these problems. Have a good day.